This video looks at sketching with asymptotic methods. So far we've looked at what is frequency response and how do we define it, and at the moment we're looking at things like how do I represent frequency response information in a helpful or graphical fashion. And in particular we're finishing off now how do we do Bode diagrams and how do we do them quickly and efficiently if we just need a sketch. Now, the previous videos have showed that if you have a single simple factor, then you can do a Bode diagram sketch based on asymptotes fairly quickly. We've also shown that you can obtain a Bode diagram with several simple factors by adding together the Bode diagrams of the underlying factors. However, we did show that although this was simple, it was tedious and clumsy. So what we want to do now is build on those earlier insights to give some sketching rules for a more general case, which are neither tedious or clumsy, and are also insightful, so they can be done quickly and they give us insight. Now you're reminded this method is based on approximation. They are sketches, not plots. If you want an exact, I shouldn't use the word sketch there, I should use the word plot. If you want an exact plot, then use a computer. So just a reminder of some of the approximation things that we've used. If you have a simple factor of this form, g over 1, g equals 1 over s plus a, then if omega is much less than a, the phase is roughly 0. If omega is much bigger than a, the phase is roughly 90. And if omega equals a, the phase is about 45 degrees. We might use these two intervals sometimes, but often we won't. What about the gain? If omega is much less than a, then the modulus of g is roughly 1 over a. If omega is much bigger than a, then we have this slope of minus 20 decibels per decade. And if omega equals a, then we have this 3 decibel offset. Now we're going to use these insights or approximations in combination with the additive property to show some quick sketching rules. Now, to show you how we're going to go about this, let's break the frequency range into domains based upon approximations for each factor. So I'm going to use an example here. You'll notice I've got g equals 3 over s plus 1, s plus 5, and so that's got corner frequencies at 1 and 5. So first I'm going to look at what happens if omega is much less than 1. There you are. If omega is much less than 1, then the first factor, 1 over j omega plus 1, can be approximated by 1 over 1, and the second factor can be approximated as 1 over 5. So I put those two together, and what do I get? I get, don't forget we had this 3 up here on top, so I end up with a gain of 20 log to the base 10 of 3 over 5, or minus 4.5 decibels. What happens if 1 is less than omega is less than, I'm afraid that should say 5, not 2, is less than 5. So if omega is between these two corner frequencies, in this particular case, 1 over j omega plus 1 can be approximated by 1 over j omega, or the gain is just 1 over omega, and the 1 over j omega plus 5 is 1 over 5. So when I put those two things in and do my approximation, what do I notice? I've got minus 20 decibels per decade as the slope. Finally, what happens if omega is bigger than 5? Well, in this case, the gain of 1 over j omega plus 1 is roughly 1 over omega. The gain of 1 over j omega plus 5 is roughly 1 over omega. And therefore, I end up with this minus 40, i.e. I get a slope of minus 40 decibels per decade. So you'll see I've broken my domain into 3 different regions. Omega less than 1, constant gain. Omega between 1 and 5, slope minus 20. Omega greater than 5, slope minus 40. And here you can see the result. So here's a frequency of 1. And then we've got 2, 3, 4, 5. So here's a frequency of 5. So I've got corner points at frequencies of 1 and 5. You'll see if frequency was less than 1, I had a constant gain, and we said that was roughly minus 4.5 decibels. After that, we had a slope of minus 20 dB per decade, and then after the corner frequency of 5, we had a slope of minus 40 dB per decade. So all I'm doing with my diagram is I'm drawing constant slope, then a slope of minus 20 decibels, then a slope of minus 40 decibels. To get the exact plot, I've done a small correction at this corner frequency. It's probably about 3 dBs. A small correction at this corner frequency, again about 3 dB. I'm not being overly precise, and then just joining it together by a smooth curve. Now remember, we only want to sketch, so accuracy to within 1 or 2 dBs is more than enough. And so you can see I can do that very, very quickly. What about the phase then? Well, again, I need to do the same sort of tricks. So I'm going to start with omega less than 1, and I find I can approximate both factors by a constant, and therefore the phase is approximately 0. If omega is between 1 and 5, then I find one factor is approximately 1 over j omega, 1 is approximately 1 over 5, so I get minus 90. I could apply a correction of around 45 degrees, but I'm probably not going to, as you'll see later. And finally, if omega is bigger than 5, you'll see both factors can be approximated by 1 over j omega, so the phase is tending to minus 180. So let's put those insights into my diagram, and you'll see what have we got. For low frequencies, the phase is 0. Between 1 and 5, my asymptotic approximation, now remember, this is based on asymptotes, it's not exact. Then we've got minus 90, and for large frequencies, we've got an asymptote of minus 180. Now what we need to do is apply some corrections. So here we're going to use this formula, which tells me exactly what the phase is: minus tan to the minus 1 of omega, minus tan to the minus 1 of omega over 5, and I need to say where do I think I'll need corrections, and clearly it's going to be in the domain near 1 and 5. So for this one I'm going to try those two values, so I need to cross that so we can see. So I'm going to calculate the phases at a frequency of 1 and a frequency of 5. So you see what you get. Here you get minus 56, and here you get minus 124. So I mark those two values there and there, and now all I need to do is use the asymptotic information, go through those two crosses, and you'll find that the curve is not far away. And remember, if we use our classic results, which we've used in previous slides, once we go about a decade away from a corner frequency, we're looking for an error from the asymptote of the order of 6 degrees for each factor. And therefore, I can get rough starting points here, rough starting points around here, which ensure that my curve is close enough, especially when I'm only looking for a sketch. I'm not looking for a plot. Let's do a different example then. So g equals s plus 1 over s plus 2 s plus 3. And you'll see now what we're going to do is gradually get quicker and show why this can indeed be a very quick method. So first of all, I've written each of the factors: j omega plus 1, j omega plus 2, j omega plus 3. And next, I've broken the frequency into the different domains based on those corner frequencies. So omega less than 1 for the first frequency, omega between 1 and 2, because that's between the first and second corner frequencies, omega between 2 and 3, that's between the second and third corner frequencies, and omega greater than 3, so omega greater than the biggest corner frequency. And now I'm going to say what happens to each factor in these domains. So if omega is less than 1, j omega plus 1 is approximated by 1. If omega is between 1 and 2, j omega plus 1 is approximated by j omega, and in fact it's j omega there after. What about j omega plus 2? If omega is less than 1, we approximate that by 2. If omega is between 1 and 2, we approximate that by 2. If omega is between 2 and 3, we use j omega, and if omega is bigger than 3, we use j omega. And finally, let's look at j omega plus 3. If omega is less than 1, we put 3. If omega is less than 2, we put 3. If omega is less than 3, we put 3. If omega is greater than 3, we put j omega. So if we put all those approximations together, you'll see we get 1 over 2 times 3, or we get j omega over 2 times 3, or we get j omega over j omega times 3, or we get j omega over j omega times j omega. So the key thing here is this last column. We've basically found the asymptotic approximation based on each factor. Now, let's work out what that gives us. So if g of j omega is 1 over 6, then we've got a fixed gain and the phase is 0. If g of j omega is approximately j omega over 6, then we've got a slope of plus 20 decibels per decade and a phase of 90. If it's 1 over third, it's a constant, minus 9.5 decibels, and a phase of 0. If we've got 1 over j omega, we've got a slope of minus 20 decibels per decade, and a phase of minus 90. So now what I'm going to do is take the information in this table to construct my gain and phase diagrams. So here you'll see we've done the gain approximation. If frequency was less than 1, we had a fixed gain, there it is, minus 15.6 decibels. Between 1 and 2, we had a slope, here it is, of plus 20 decibels per decade. Between 2 and 3, we were constant at minus 9.5 decibels, and then we had a slope of minus 20. So hopefully you're beginning to see how quickly we could do this. We can just basically sketch the slopes. Now, ultimately, we want to get an accurate gain diagram, but if you look at the differences in values here, so if I just mark the differences down here, that's 6 decibels. And I've used a particularly expanded scale here. Usually, if you can sketch to within 2 or 3 decibels, you're doing quite well. So as soon as you sketch any curve which follows these asymptotes, give or take, you're not going to be far away from this red curve here. However, if you want to be sure, choose a particular frequency, let's say this one here, 2 equals omega, and find an exact value to hang the plot on. What about the phase plot then? So again, you'll see we've simply put the phase information. We've said if omega is small, 0 degrees, between 1 and 2, 90 degrees, between 2 and 3, 0 degrees, and then down here, down to minus 180. Now, you can probably guess, because these frequencies are close together, there's no way the phase is actually going anywhere near 90. So what we need to do is add a few exact computations in this region here, because we're not sure exactly what the phase is doing in that region there. So what frequencies am I going to choose? Well, let's choose omega's 1 and calculate the phase, and there it is, minus 45, minus 26, minus 18, and you'll see that's approximately 0. So there we go, 0. If I choose g of j3, you've got 71 minus 56 minus 45, and that's going to be approximately minus 30. So let's mark that down, and there it is. And once you've got those two plots, you're pretty much there, because you can see that not much is going to happen along here, and then after that, once you've got a smooth curve there, you've got to pretty much follow to the asymptotes, and the error down here after a decade is going to be of the order of 6 degrees. So you can get a curve which is close enough, and remember, you're only trying to get a sketch, you're not trying to get a plot. So this is enough information to give a clear indication of what the Bode diagram is doing. Now one final example, and we'll do this one a bit more quickly. So I've got g equals s plus 2 over s, s plus 1, s plus 4. First thing to do is to mark the key domains. So I've got omega less than 1, 1 less than omega less than 2, 2 less than omega less than 4, and omega bigger than 4. And that's based upon the corner frequencies. And now I can do the approximations. So this one, j omega plus 2 will be 2, 2, j omega, j omega. J omega plus 1 is going to be 1, j omega, j omega, j omega. J omega plus 4 will be 4, 4, 4, j omega. And don't forget, I've not put it in this table, we've also got this s, which is another j omega. So the total slope for omega less than 1 is going to be minus 20 decibels per decade, and that's all going to come just from the s, because the other terms are constant. Between 1 less than omega less than 2, you're going to get minus 40, because you've got the s and you've got this s plus 1. Between 2 less than omega less than 4, you're going to go back to minus 20, because you've got the s plus 2 in the numerator. And then for omega greater than 4, you'll go back to minus 40. And the phase just matches that. You'll have minus 90, minus 180, minus 90, minus 180. Now, we need to know how to initiate the gain plot, and that's not always obvious, because clearly with an integrator you've got infinite gain at low frequency. So we need a practical way of deciding where do we start the asymptotes in order to use the asymptotic approximation. Now what I recommend is you basically use the lowest corner frequency and use the asymptotic method at that frequency, and that will give you the correct value. So here's the transfer function. G equals j omega plus 2 over j omega plus 1, j omega plus 4, and we're going to use the asymptotic approximation at the lowest corner frequency. So in other words, if omega is less than 1, then we've written that g of j omega is approximately equal to 2, so j omega plus 2 is just 2, times omega, that's for the j omega, times 1, that's for the j omega plus 1, times 4, that's for the j omega plus 4, which gives me 1 over 2 omega. So that's the approximation for small omega. Now, at omega equals 1, this is going to give you a half, or minus 6 decibels. So your asymptotes will go through minus 6. Now, having done that, we can now show how this method will combine to give a very fast sketching method. In terms of exact computations, I'm not going to bother with the gain plot, because it's usually difficult to sketch when you've got a range of 60 to 80 decibels. You can't sketch more accurately than 3 or 4 decibels anyway, so it's hardly worth it. With the phase plots, you're going to need 2 to 3 exact computations in order to get a smooth plot near the corner frequencies. So you're going to need to calculate this formula exactly at 2 to 3 places. So that's the exact statement for the phase of the system. Now, just to re-emphasize, if you really need an accurate plot, you shouldn't be bothering with all this sketching. Just go and use a computer. So the purpose for practicing sketching is to gain insight and understanding. Here we go then. So I've now thrown away all my tabular information, which you can go back and use if you want, and I'm going to say, how can you get the result going straight, okay, from the transfer function? So I know I had a 0 at minus 2, so I'm going to mark that was 2. I had a pole at 1, there's 1, and a pole at 4. Now if you look at the asymptotic approximations, you'll see that whenever we go through a pole, the slope changes by minus 20 decibels per decade. And we also said that the plot started at minus 6 when frequency was 1. So we said to the left of there, we said the slope was at roughly, well not roughly, was at minus 20 decibels per decade. So we needed to find a start point, that's that cross at minus 6 for omega equals 1. And then we said for lower frequencies the slope was minus 20 decibels. When you go through 1, you'll notice it's a pole. So the slope is going to go now down, and I'm not going to do this too precisely because I haven't a ruler, to minus 40 decibels per decade. And then it's going to go back to minus 20, and then it's going to go back to minus 40. So all I'm going to do with this sketch is make sure that I get those slopes as close to exact as I can. And that's relatively straightforward if you've got a ruler. And so there's my game plot. You see, all I've done is I've gone through each corner frequency, and at the corner frequencies I've changed the slope based upon, is it a pole? I go down by minus 20 decibels per decade. Is it a 0? I go up by 20 decibels per decade. What about the phase plot? I can use a very similar insight. So it starts at minus 90 because of the integrator. I get to the first factor, which was a pole, so I now go down to minus 180. I then get to the next one at 2, which was a 0, so I go back up by 90 degrees. I then get to the next one, which is a pole, and I go down. Now you might think this looks a bit messy. However, what it tells me, if the asymptotes are going up and down a lot quite close together, I'm essentially going to ignore them, because it means the poles and zeros are quite close together, and therefore the impact is largely going to cancel each other out. So for example, this S plus 1 and S plus 2 are quite close together, so their phases are going to almost cancel for anything not close to omega equals 1 and 2. So having done that, what I now need to do is do a few exact computations. So where do I need exact computations? Well, probably in this region here. So let's do a few. If I do g of j1, I get minus 123. There it is. G of j4, I get minus 147. So let's mark there. There it is. And that's probably enough, because I know with this S plus 1 I can see they're going to nearly cancel as long as I'm not close to that. So pretty much the behaviour will there be dominated by the S plus 4, certainly for large frequencies, and perhaps even for small. So I'm going to end up with a sketch that does something like this. Okay? And that will be good enough for me to get an idea of what's going on. So in conclusion, the video has presented some simple sketching rules for Bode diagrams for systems with several factors. It's shown that an accurate sketch can be determined by noting asymptotic information, then adding a few explicit computations near the corner frequencies. There are other ways of doing sketching, and you will see that in the books. In my view, it's not worth spending too much effort on this, so ultimately you'll see in the tutorial sheet that follows that I recommend you do it very quick and simple, and if that's not good enough, get a computer. And finally, in general, the plots only need to be accurate in the region minus 20 to minus 180 degrees. It will be evident why later, and that's where you should focus any numerical